So if a circuit contains dependent sources, then we have a little bit more work to do to calculate a Thevenin resistance using this shortcut approach. So what we can do is deactivate all the independent sources, but the dependent sources have to basically stay online and stay connected. So once we've done that, we'll end up with a circuit that contains some dependent sources. We then apply a test voltage or a test current into those terminals, basically inject some energy, and we monitor what will happen. And so we then can calculate the Thevenin resistance using Ohm's law. So basically calculate the resistance using Ohm's law depending upon the test voltage and test current that will actually flow into those terminals. So let's take a look at this example here. We have a dependent source which is controlled by the voltage across this resistor. We'd like to analyze to find the Thevenin equivalent looking into this terminal here. So how can we actually do this? Well, step one is to deactivate the independent sources. And there are no independent sources in this circuit, so nothing to do. So no independent sources. No independent sources, nothing to do. Right. Step two is to apply a test voltage or a test current. So for this particular example, I'm going to apply a current. It doesn't matter, you could also choose to apply a voltage. And basically what that means is I'm going to take these terminals and I'm going to connect a current source into them. So let's just redraw the rest of our circuit so that we can then go ahead and analyze it. So we had current source Vx divided by 6, then our resistor and another resistor, and they were 20 ohms, 10 ohms, and our voltage Vx is defined across that resistor. So our test current, let's just call it IT for test. And now I would like to analyze, well, what is the voltage that appears across these terminals? So that would be a voltage here. We'll call it Vt for vtest. So if I know the test current and the test voltage, I can then calculate the Thevenin resistance looking into these terminals. So to analyze this circuit, I'm going to use a nodal analysis. So I'm going to basically define a reference node and then choose node V1 to be the voltage of this node at the top here. And notice in particular that this V1, this is actually the same as the test voltage. So actually to keep this nice and simple, I could even call this as Vt, the voltage of this node here. So let's go ahead and write Kirchhoff's current law at this node labeled as Vt. So the currents leaving down the left-hand branch will be Vt minus 0 divided by 20 ohms plus 10 ohms. The current leaving the source, well, actually the current is entering, so it's a negative Vx over 6. And then there'll be a current leaving through that 30 ohm resistor, so that would just be Vt minus 0 divided by 30. And then of course the test current, which is entering, so I'll write minus It here, and all of that is equal to 0. Now what can I say about my voltage Vx? Well, Vx is a voltage divider based on this set of resistors over here. So using a voltage divider equation, I have that Vx is proportional to Vt, but multiplied by the resistor over which it's measured, that's 10 ohms, divided by the sum, which would be 10 plus 20. So this is Vt times 10 over 30, which is just Vt divided by 3. So I can substitute that back into my first equation. So substitute Vx into, let's give it a name. Let's call this one here equation 1. So substituting Vx into equation 1. I will have Vt divided by 30, I'm just cleaning up a little bit as I go, minus Vx, so Vx was Vt over 3, and all of that is also multiplied by 6, so it's 3 times 6, plus Vt divided by 30 minus It is equal to 0. Let's simplify this one a little bit more. So I will have for my VTs, I can kind of collect like terms on this. So this is Vt times 1 over 30 minus 1 over 18 plus 1 over 30 is equal to It. Now we just get out our calculator and we analyze that the term here in parentheses is, so 1 over 30 minus 1 over 18 plus 1 over 30 is 0.01111 recurring decimal. Vt is equal to It. Bringing that to the other side, so just 1 divide that number will give me 90. So it is just Vt is equal to 90 times It times my test current. So looking at this circuit now, I have a relationship between the voltage and the current kind of entering into these terminals. So looking at my steps for what I need to do, I've already done this applying a test voltage or a test current into the terminals. The next step is calculate the Thevenin resistance, basically using Ohm's law of this information that I have already calculated. So this tells me that the Thevenin resistance is going to be my test voltage divided by my test current. So that one is 90 times It divided by my test current was It, which is just 90 ohms. So another thing that I can determine from looking at this circuit, right, because there were no independent sources here, we actually can immediately determine that the Thevenin voltage must be 0. So no independent sources means nothing to do here as far as deactivating, but it also means that the Thevenin voltage is equal to 0. So you could have analyzed this as open circuit, basically done some, say, nodal analysis on this top equation, on this top circuit, and you could have seen that there will be basically 0 volts here. The other way that you could have seen that is basically, well, if there's no independent sources in the original circuit, then there can be no independent sources in the simplified circuit, because they're supposed to represent the same thing. So if there's no independent sources in the beginning, and we clean it up, there still has to be no independent sources. So because of this information that we have that the Thevenin is equal to 0 volts for this circuit, then we can actually draw what would be the Thevenin equivalent. So remember, normally we would have a voltage source here and a resistance. And we've calculated that the resistance is 90 ohms, and we've calculated that the voltage source is 0 volts. Well, remember, we also learned that a voltage source of 0 volts is the same as just a short circuit. So our Thevenin equivalent is actually just this, with a single resistor, which is 90 ohms. So out of all of this circuit here, all of this collapses down into just a single resistor, and that single resistor is just 90 ohms. So that's the final simplified form of our circuit.